Right. Should start again. So, online people, can you still hear me? Yes, good job. All right. So, this was a long introduction about what we are planning to study and my expectation for the homework and the course in general. So now let's start the actual course. So the first is chapter one was all about those energy distribution, like what kind of energy we are using and why the building the case for basically why we need renewable energy, right? So in those renewable energy, whether wind or hydroelectric, all those machines that rotate, the point is that in order to rotate it, we need to give it angular momentum. Angular momentum. Just like if I want to kick a ball forward, if I'm playing soccer and I want to kick a ball, I have to give it linear momentum. Okay? I need to give it linear momentum. So I kick it with a force. So the same thing for all those turbines and even pumps. If we're gonna do a hydroelectric storage. So whether it's a pump or a turbine, anything that's rotating, you need to exert torque on it. Okay? So in this chapter, he's trying to explain to you how you can calculate that torque. And just like the Newton's second law that tell you that the force equal m dot dv by dt, the change in the link or m dv by dt, in order to give a change of uh, linear momentum, you have to exert a force. He will tell us that in order to change the angular momentum, you have to give a torque. So torque will be m dot r2 v theta 2 minus r1 v theta 1. Okay, so what is this rv? This is the equation for calculating the torque on the machine, whether it's a turbine or a pump. So he's trying to explain to us what is this v theta and what is the r. First of all, what is v? V is the velocity. And the chapter start, we need to make sure that we understand there are two different velocities. There is the absolute velocity and there is the relative velocity. Okay? So if I am in a bus and I'm walking in the bus while the bus is moving, I have two velocities. My velocity relative to the moving bus, that's V relative, and then my absolute velocity relative to what? To someone standing on the street. You will see my velocity as my velocity in the bus plus the bus taking me. Okay? So because those machines are rotating, there is also V absolute and there is V relative. Okay? So like those propeller, whether it's a propeller for a jet, an airplane, or actually this is, if it's actually a plate on a wind turbine. There is the absolute velocity of the air coming toward the wind turbine. And if this was a propeller, it would be the velocity of the propeller and the airplane carrying it, moving into the air. That's the absolute velocity. Okay, so that velocity is this v1 coming toward the plate standing like this. Here is v1. But because the plate is also moving, and it's very easy to calculate that velocity. How much is the velocity? Omega r. Where omega is this omega, how many rev per second? Wait, it's actually SI. It should be, omega should be in what? What's the unit that we should use for omega? Radian per second. That's the right unit use. But what problem do you think the problem statement will tell you, or the supplier will give you, or the manufacturer will tell you? RPM, round per minute. So how can I turn RPM to radian per second? Round per minute, that is 2 pi. So if he says 60 RPM, how many radian per second is this? 60 RPM would be 60 times, every round is 360, which is 2 pi. And this is 60 round per minute. So how many does it do per second? You divide over 60. Radian per second. Makes sense? If he's doing 60 round per minute, I bet he's doing 1 round per second. Right? So the conversion is this. You multiply by 2 pi and you divide over 60. Good. So omega is gonna be radian per second, huh? And r is the radius of this place. So obviously, this guy have a smaller radius than this guy. So this is amazing. This actually means that in some of those compressors, the tip could be moving supersonically, while the hub, or between the hub and the tip, the speed could be lower than supersonic speed. Why? Because this r, the radius. But what that means? It means that the velocity of the plate, U tip and U hub, could be different. Okay? So this is V absolute, V1. This is the wind coming. But depending on the velocity of the plate, V relative will be different. Different in magnitude and different in direction. Okay? So what is this equation? How did we come up with this diagram? Because that's the hardest thing. So V absolute is V relative plus the velocity of the plate. Okay? Some book write V equal W plus U, like your undergraduate fluid mechanics book, the one by Okishi, the one that you had in engineering science, what, 233? Or right now it's called ME 333, I guess. You will call V relative as W. Okay? Whatever the symbol you use, I would say V absolute. If I were you, I will just like spell it. I would say V absolute equal V relative plus V plate. Okay, so this is like the bus velocity, and this is your velocity relative to the bus, and this is your velocity with respect to someone who's standing over here. This is your V absolute. So it's very clear that V absolute is your V relative plus the V that's taking you around. Okay? Make sense? Makes sense when everything is moving in a straight line. So obviously, my absolute velocity is my velocity with respect to the bus plus the velocity of the bus. But what makes things complicated is that in this example where this plate is doing like this, and he's running around, the velocity is kind of like 3D. So V absolute is coming like this. And where is the velocity of the plate? In that plane, it would be tangential like this at 90 degrees. This is 90 degrees. And it's coming with omega r. Okay? If he's rotating like this. So, I mean, it's like this, V plate. Again, this is 90 degrees. So how can this equation work? V absolute is V relative plus V plate. It must be that V plate is where? Where can I write V plate? I want to say V relative plus V plate equal V absolute. What can I add to this guy? This is V plate sitting at 90 degree here. I know it's hard to imagine it's three-dimensionally, but what can I add to this guy so I can get this guy? It must be this guy. This must be V relative. Okay, so how we can do this nicely? So if the plate is rotating like this, and that's, look at me. If the plate is rotating, this is my X and the plate is moving like this. And here is V wind, absolute. The wind is coming, the wind will always come normal to this thing. Why it's always coming normal? Because that brake rotor actually moved to face the wind. You would think those big turbine is like stuck to the north or the east. No, they are sitting on a tower and that tower rotates. They rotate, and actually that immediately tell you there's a problem with like, so the cable generating the electricity, can it twist over itself? Yes, it can. And that's why that turbine, once it turns one round, it cannot keep going. It has to unwind itself to go to the other place. So I mean, he cannot just like keep spinning around himself. Point is, here is my X, here is the plate rotating like this, and V absolute is coming this way. V relative would be this way, omega R. So where is V relative? It's going to come like this, right? And so that V relative in this plane, it will be different from, say, V relative here. Why? For the same V absolute, V relative is different. And so that V relative would be different angle and different magnitude. So that's what happen. That what make different section of the plate look different, because each one of them are facing wind coming from different direction. Not because the V absolute is different, the wind is the same on all the plate. It's just because the rotation is different, V relative become different. And that explains why long, what is, that explains why long turbine plate look what? A little bit twisted, right? So why it's a little bit twisted? Because it's trying to accommodate the direction change of V relative, okay? So you would think that the turbine is designed to meet V absolute, but no, it's actually designed to meet V relative, this W, okay? And that's what I'm trying to draw with this. Of course, in short gas turbine plate or compressor plate, you don't see that twist because there's not enough difference in omega R. Omega R at the hub and omega R at the tip, almost the same. So the plate didn't really have that much change. Okay? But when you go home today and you look at the ceiling fan in your room, you will notice that does the turbine, that the plate has any twist in it? No, it does not. It should have some twist in it, but actually they make it just out of one big plate. I mean, the whole thing is twisted. Yes, but there is no twist in it. The plate is not twisted to meet different relative velocity. So they are compromising part of the plate, right? Not all the plate are meeting the wind in the right direction. Okay, because that plate is really long, right? There is difference between the velocity at this and this. in our ceiling fan. But the ease of manufacturing, you know, is they are probably thinking, well, maybe the energy is not going to change that much, and besides, people are just happy seeing this thing spinning. They are not really caring about how much air it will come out, and it's not really high pressure, you know, that we have to worry about it, and so on. What happened? So I have to get out of the drawing mode. Okay, good. Okay, so this is the equation, huh? V absolute is V relative plus U, and things are a little bit easy when it's everything is in line. This is sprinkler that he's shooting water behind, right? And as a result, he move forward. So the one thing we need to remember is that when it comes to, that's the first thing here, when it comes to the flow rate, m dot, which is, what's the mass flow rate? Rho time the volumetric flow rate. The density time Q, right? So m dot in kilogram per second is rho multiplied by the Q, where rho is in kilogram per meter cube, and Q, and sometimes people call it Q dot, but it's really Q, that's meter cube per second. So this is mass flow rate, and this one is volumetric flow rate. Right? Then the Q can be further written as A times V, right? So rho A times V. And the question is, what V we should use? Should we use V relative or V absolute? Always V relative when it comes to m dot. Excellent. Who said that? What's your name? Excellent. So when it comes to m dot, you should use V relative. Okay. When it comes to that equation of the torque that we're going to drive in a minute, m dot R2 V theta 2 minus R1 V theta 1, this has to be absolute. Okay. So continuity, you use the relative velocity, and torque, you use the absolute velocity. Okay, and so the example that I usually give to myself to remember, like which velocity I should use for m dot, I say, imagine if you are driving your pickup like this, and your friend is trying to be funny, and he's shooting water from his garden hose in your truck, and he's shooting it at, you know, whatever V jet meter per second. And you are driving your truck at V car over here, and you are trying to figure out how much water will actually end up landing in your truck. And you're saying, well, the mass flow rate that will land m dot is rho water A V jet, where A is the cross-section area of that water. But if you are moving with the same velocity as V jet, nothing will land in your truck, right? So it's never, when it comes to m dot, it's not the absolute velocity that matters. It is v relative. So this should be v relative, v jet relative. So how can I get v jet relative? Well, v jet absolute is v jet relative plus v car, right? And so it's very clear that v jet relative become v jet then v jet relative become v jet absolute minus v car. And so since there is plus and minus, we probably need to say what is the positive direction. Okay, and so if things are moving in that direction, it become plus. If it's moving in the other direction, it become negative. Okay, so let's say he's shooting it at 10 meters per second. That would be plus 10. And this car is moving at 8 meters per second. That's plus 8. So you come here and say it's 10 minus 8. So the velocity actually going to be 2 meters per second. Okay. So this become a little bit more involved when it's like in 3D, right? But the point we want to make is that when it comes to m dot, you use always v relative. Okay. Very good. So that equation in our chapter 2, the torque is m dot r2 v theta 2 minus r1 v theta 1. So he is actually calling it, v u. Why? So that view is v theta. What is v theta? What he's talking about? Most textbook, they actually call it v theta. Okay. We'll see why in a minute. It's the same thing, right? You have to shut this down. Okay. So this big fancy equation, it just, I loved writing the equation this way when I was undergrad because it made me feel smart. Because like, look, it have partial differentiation and it have triple integration over the volume, and it's basically have control the integration over the surface, and it have dot product in the middle over here. But that fancy way of writing the equation, this is like for general, water spinning into a machine and leaving from different places, and this is the general form. But it boiled down to just this guy in red, where you have only one exit and one inlet. The exit is 2 and the inlet is 1. So for example, water coming into a pipe and leaving at here. So this would be 1, this place would be 2. Okay? And so what are you trying to do? You are trying to calculate when the water come in like this and leave like that, how much torque does it put on that joint? So that you would calculate, say, how much welding I need in order to make it resist that torque before it spin. Or I'm trying to anchor this pipe. They are telling you this pipe always break, and we want to figure out how much force does it take to hold it. So you want to calculate how much torque. So how do you calculate the torque? If I said how much force does it take, if someone is like standing and holding this pipe in place, and I said, calculate for me how much force does it take to hold this pipe stationary? What? So here is V1 and here is V2. And I said, well, how much force do we need to apply on that wall so that this elbow does not break into the wall? And you would say momentum equation. Force equal m dot v2 minus m dot v1. And it's usually the same m dot, because before you apply the momentum equation, usually you apply the continuity equation. And the continuity equation would say what? M dot 2 equal M dot 1. Why? Why M dot 2 equal M dot 1 most of the time? Well,
It's the same mass flowing through the pipe.
yeah, what I'm saying is like why it's usually the same mass. That's my question. Why usually it's like the same mass going through the pipe? Huh? Yeah, because in most engineering application, we build things for steady state. We don't build pumps and compressor that will explode in few minutes. Like you wish that everything come in will have to leave. Otherwise, if they don't leave, someone is being stored and this thing will blow up. So most application is steady state. So for steady state, m dot n equal m dot out. Unless you are working for a nuclear reactor study where you are trying to duplicate the accident that happened, maybe at that point things were coming and were not leaving, and that's why the explosion happened like 3 minutes later. So most of the time m dot 2 equal m dot 1 equal m dot. And the momentum equation will be this: F is m dot v2 minus m dot v1. Okay? And so if this is the anchor point, and this is, say, our x-axis, and this is our y-axis, then we can write this equation in the x direction and the y direction, right? That's why I have a vector here and here and here. So in the y direction, Fy would be m dot, and it would come to V2, you would say, let's say like this was like 20 meters per second, and this was like 5 meters per second. And how did we come up with this number? Probably A1 V1 equal A2 V2. I mean, initially there was what? There was rho and rho. Because m dot is rho AV. And what all those things that you said about absolute velocity and relative velocity, why you are not using it over here? Because the pipe is not moving, and therefore V relative is the same as V absolute, right? And so rho cancel with the rho. Why? Why rho 1 is the same as rho 2 if this was water? Yeah, because it's incompressible. So rho, this become rho Q1 equal rho Q2 equal basically rho Q. Okay. So anyway, if this was 5 meters per second and this was 20 meters per second, huh? So in that equation, we will say Fy is m dot multiplied by, when it comes to V2, it will be minus 20. Why minus 20? It's a negative direction. And then minus, and then with V1, you get minus plus 10. Why plus 10? Because it's going up in the right direction, right? V1 is plus, V2 is negative. And the equation is F is m dot V out minus m dot V in. That's the momentum equation. Make sense? If not, doesn't make sense, ask me now. Did I say 5? Yes, sorry. Totally right, sorry. So you would see how Fy is now m dot multiplied by minus, I guess, minus 25 m dot, right? Minus 25 m dot. And you can see how V1 and V2 did help each other to make that force requirement even stronger. Why? Because V1 in the entrance is pushing up, and V2 at the exit is also pushing up. Because V2 is acting as if it's a rocket engine. You're shooting behind and he's sending it up. But V1 is basically pushing up, right? So this is of course assuming that the force is only because of the wall support. If you also have pressure force, if there was also a pressure force like B1 gauge area 1 and B2 gauge area 2, you will have to add those two guys also in the force balance. It's not just the wall that's pushing, but also pressure are pushing on the pipe, right? But the point is that equation, if you take the moment of that equation to calculate now how much torque is actually being applied, say like you are holding it here and you are worried that will he end up twisting the weld because the angular momentum that he's exerting. So that equation become, rather than, and again, this is the x-axis and this is the y-axis anchored from this, then the equation become torque m dot r2 v theta 2 minus r1 v theta 1. Okay, so now what is v theta? So because it's torque, the velocity can get split into two components, radial component and tangential component. This is called VR, and this one is going to be called v theta. Where is this coming from? In any coordinate system, if the velocity is like this, you can split this velocity into Vx, V1x, and V1y. The x component of the velocity and the y component of the velocity. But that same velocity, V1, can be split into a radial component, which happen to be all V1, and the tangential component, that would be normal. But if V1 is all radial, like this, there is no tangential component. Imagine if a hose, the water is coming from a hose radially everywhere. Will this guy twist? He will not, because it's all radial. But if he has a tangential component, he will have a torque to it. So what I'm trying to say is that V1, the component in the radial direction does not want to twist the thing. It's only the tangential part that want to spin the elbow. And so this is the tangential component of it. Okay, it will be clear when we start seeing on water pump. Okay, so let's go this example. This will explain to us what is V theta and V radial. So this is a turbine, hydraulic turbine. Water come at the inlet here, V1. Okay. This is the inlet, and it leaves from the hub. And so the water, again, those machines is all about applying a torque. Okay, we need that flow rate coming in. If we send all that flow radially in, like your water tap, if the water come radially into the sink, it will go down. I take this back, because in the water tub, actually the water never go radially in. The water come with a swirl. Does anyone know why in the water tub the water swirl? And amazingly, it will always swirl in the same direction. So do this experiment at home. Watch your water tub swirl happening and inspect it day after day. You always find out it's always happening in the same direction. Does anyone have a guess why? The position on the northern hemisphere or the amazingly, right? So here is the Earth, and because it's rotating like this, over here, the water tub will rotate like this. While here, if you are living south, it will rotate like this. This is sounds silly, but he just confirmed to me that if you ever watch it, that it's rotating the other way. Anyway, back to our story. So so in order to rotate that machine, in order to give it a torque, the water coming in into the plate, hitting the plate, it cannot just go straight. It needs to come with a twist. And that's why V1 come like this. Okay? We will see how do they build machine like this, but the stator or the water plate, the plate directing the flow into the turbine, need to send it with a swirl. Okay? And as a result, V1, if you see V1 over here, that V1 is not, and that's the center of the machine. V1 is not shooting like this. If it shoots like this radially, it will come in without turning the machine. But instead, what do? You can see how they are sending V1 with 30 degree to the tangential direction. So this is 30 degree and this is V1. So this component will help turning the machine or not. Yes, it will. That's actually the only component that will help, because that component, the radial component shooting down into the center, will not really help. So V1 cosine the 30 degree, that is the tangential component. And V1 sine 30 degree, this one is the radial component. So when it comes to that equation, torque is m dot multiplied by v theta 2 and v theta 1. What is v theta 1? It's the V1 cosine 30. Make sense? So in my sketch over here, and if this is V1, it's very clear why I'm going to call this V1 radial, right? And it's also clear is why I'm going to call this V1 theta, because in Cartesian coordinates, X and Y, but in polar coordinates, it's R and theta, right? Make sense? Tell me if you are not comfortable with it. So it's called V1 theta. So now why the book call it V1U? And it's the only book that I saw that call it V1U actually. Why does it call it V1U? Because it's actually, if you want to calculate U1, that's U1. That's omega R1, where omega is this and R is the radius. So because the V1 theta seem to be in the blade direction, they call it V1U. Okay, but they are unique in doing this. So here are the plates. Okay, and so once the flow come and hit those plates, he will now see, you can see he's coming with a twist. So he will end up spinning the plate, right? And then he would leave from the middle pipe here in the middle. If he leave with a little bit still twist in it, so we give him a lot of twist initially, right? So he's coming with big V1, big V1 theta. He comes with huge twist. And if he managed to leave with a little bit of a twist, did we lose our money or that's okay? We lost our money. We should consume all of the angular momentum that it came with, right? If I'm kicking a soccer ball so hard After I kick the ball, what should happen? If it was really efficient, my leg should stop after I kick the ball. Like all my angular momentum was given to the ball. If my feet keep going afterward, there's some energy that's lost in it. So that makes sense then why the torque is m dot r2 v theta 2 minus r1 v theta 1. So this part is kind of, did you leave anything left? Like if you come into college and you have like, say $10,000 in saving account, and then you leave college and you still have $2,000, we failed. We didn't take all your money. We should leave with zero money so that the system is very efficient. We consume all your cash, right? So and if it's a good design, in the problem they will tell you that R1, sorry, V theta 1 is zero, right? They will basically, how they will tell you this? They will tell you leave all radial. I just touched one time. What happened? So they will tell you like this. Water turbine with radial velocity has the dimension shown. The absolute exit velocity V2 is directly radially inward. So when V2 leaving is directly radial inward, that means that V theta 2 is what? The absolute exit velocity V2 here is directly radially inward. That means that V2 is all radial. So what? How much is V theta 2? How much is the tangential component of V2?
0.
Zero, because it's all radial, right? Very good. Okay, now the only thing that's missing in this problem is, again, if you remember the equation, what did we say? The torque is m dot r2 v theta 2 minus r1 v theta 1. So what's missing is m dot. How much is m dot? Rho a v. What is the area? This area. The circumference times the height, h. So the area is 2 pi r1 times h. And the v should be relative and should be normal. So that's the second thing about continuity equation. The velocity component that you use for m dot is tangential, sorry, it should be relative and normal. The velocity needs to be normal to the area. So which velocity should I use to calculate the m dot? Should I use v1? Should I use v1 theta, or should I use v1 relative? To calculate the m dot, should I use v1 or v1 radial or v1 theta? Which velocity is normal to the area? Radial, v1 radial. v1 radial is normal to that area. Okay, so to recap, what did we learn today? We learned that to calculate the torque on a pump rotor, or a pump or a turbine rotor, or any turbine machine, the equation for the torque is m dot times r2 v theta 2 minus r1 v theta 1. What's v theta 2 and v theta 1? Those are the tangential component of the absolute velocity. The tangential component of the absolute velocity, right? And to calculate the m dot, it's rho AV. What V? The V normal to the area. Okay? So I give you that example about the truck and how it has to be relative. Amazingly, in turbo machines, here is the relief. So I stick with what I said, that it has to be relative. But here is what's funny. V1, the radial component of the relative velocity in term machines is always equal to the radial component of the absolute velocity. So because I always want the radial component to calculate the m dot, I always want the radial component to calculate m dot because that's the one normal to the area. Huh? It doesn't matter whether I use the absolute velocity or the relative velocity to calculate the m dot. So why is that? For a free homework problem. If you answer this right, you get a free homework problem. So your cat can die and you still will be able to get full homework because you don't have to do the homework. So here is V absolute, and here is the U, okay? And where is W? W would be, so to calculate W to be like this, right? Let me do this better for you. I know we are running out of time, but this is, think about this and send me the answer by email. So here is V, here is U, here is W, relative velocity. So the question is, why W1 radial is going to be always equal to V1 radial? Why the radial component of the relative velocity is the same as the radial component of the absolute velocity on a term machine. And therefore, when it comes to m dot and it's rho a v, it doesn't matter whether you're going to see v1 normal or you're going to use w1 normal. That's my symbol for normal. Why? Why it's always the same? You understand the question? Send the answer in an email to me. You get one free homework. Thank you so much. I'll see you next week. No homework, by the way, for the first week. So don't worry about the homework. Question from online? So if none, thank you so much and have a good night. Bye.